So what are these common crystal structures? And we're going to see that when we think of ceramics, the structural elements to ceramics become much more complicated than what we saw in metals. In metals, we really held things to three basic crystal structures: BCC, FCC, and HCP. It's not quite how ceramics worked, and part of that, if we really want to think about it, comes back to ceramics in and of themselves. The idea behind ceramics is much older than metals. And so over time, the way to identify and the categorization and the characterization of ceramic structures developed in a different way than metals. And so they weren't limited to just those types of crystal structures. So what we tended to see is, depending on the number of cations and anions, it gives us certain crystal structures. And so what we see here is if we have an equal number of cations and anions, we have this AX type structure. We see cesium chloride as a common one, zinc blende rock salt. And this is where I'm really coming from. We see sort of the anion packing can take into these cubic type structures, but when we start referring to crystal structures in ceramics, what we're really going to be referring to are very much names that we come to, much like when we talked about hardness in the Mohs scale. For hardness, what we saw was there were examples, and ceramists tend to deal in much the same way. A rock salt structure is what they would call a similar sodium chloride type structure. And not only sodium chloride has this structure, but other types of ceramics do. Cesium chloride type structures. Look at it. What is it? It's, for the most part, looks like a BCC structure to me. Zinc blende looks like the anions are sitting in an FCC type structure with the cations placed in different places. So what they call a zinc blende structure. A fluoride structure is this sort of AMXP type. These are all AX types, so there's an equal number of cations and anions in the chemical formula. Fluoride structure is this AMXP, or you get into ternary type structures even, and what we call a perovskite structure. This is a barium titanate perovskite structure. I always like to, at this point, sort of say, perovskite structures, people thought about them. They were unique. Barium titanates are an area of pretty significant research within the ceramics community and for their electrical properties and other properties they may have. But the perovskite structure really came to sort of prominence with the identification and the discovery of high temperature superconductors. And so this goes back into the 80s, early 90s, where the attempts were made to try to increase the temperature at which superconductivity took place. Now, when they're talking about high temperature superconductivity, it typically is falling in the range of where you have liquid nitrogen. So high temperature is a relative term. It's a lot better than 4K, where you need liquid helium to develop superconducting properties and materials. But superconductivity is still out there as a major goal for energy transmission and energy savings, because you can get conduction of electrons, or electrons can conduct or flow with no resistance. And without that, you have a power source that seemingly could go on forever. So these anions, they also close pack, these anions and cations. And so if you think about a cation-anion combination, you can have a tetrahedral position or an octahedral position, and it depends on the coordination number. So tetrahedral is 4, octahedral is coordination number of 6. And so we start thinking back to when we were thinking of crystal structures for metallic systems. What we have is much the same thing here, with these spaces where we can place a cation in an anion plane. And so very much like the close packing for the FCC, the ABC type of combination or stacking, and for the HCP, the AB type stacking. So what we can have is, going back to the sodium chloride structure, these ceramic structures depend on the stacking of these close packed ions. We saw that in an FCC structure, and if we go back to the rock salt structure, we see that the anion packing is already FCC, so we know it's going to be close packed. And so when we start seeing of these close packing, we're going to have to start with that type of FCC anion structure. And we can see in there that cubic symmetry, it's FCC, all the planes sit on this 1-1-1 type plane, and the cations basically sit in a coordination number of 6. So they have 6 nearest neighbors as we start looking at it. We fill all these positions, and so the anion to cation ratio is 1. And so that's how the close packing in the sodium chloride structure sits. Now, let's go back even further when we were talking about crystal structures. We knew that based off certain numbers that we had, we could calculate the density based off the atomic packing in metals. We can do much the same thing with ceramics. And so we can calculate the theoretical density of a crystalline ceramic material just from its unit cell data. Sort of the number of formula units within a unit cell, the sum of the atomic weights of the cations and the anions, and then the volume of that unit cell. So where does that volume of that unit cell come from? Something you'd be given, but if it's an FCC anion unit cell, you already know how to find the volume of that unit cell. And as always, we have Avogadro's number. So you have a couple of homework problems on this. Typically, you'll be given that, but what you tend to find is ceramics, it's sort of like if you pick up a brick, feel the weight of that. What you tend to see is you have a certain theoretical density for ceramics. Ceramics don't always meet that theoretical density because they are pretty much full of different pores and porosity. So a brick of a certain size compared to a lead or something with a higher density is going to be different. So ceramics are typically used, a lot of times for their rather low density and some of the properties they can get for that low density. So if you think of the space shuttle, they lined the outside of the space shuttle with ceramic tiles. That was primarily a heat transfer mechanism, but to keep the rocket small, to make sure it was maneuverable, to make a lot of things happen, you had to have lightweight. The ceramic tiles added that lightweight as well. So what we can see is we have close packing. So a lot of the crystal structures, a lot of that crystallinity we had talked about with metals sort of comes forward in ceramics, just a little more complicated because we're not dealing with pure elements in our structures. We're dealing with compounds. And so we can have a collection of different anions and cations making them up. Now, this leads to different types of defects, and atomic or point defects are really what are going to drive ceramics. And so the other thing to keep in mind in ceramics, and I would really note this here, is with these defects, you always maintain charge neutrality. That electroneutrality concept for ceramics always stays around. But what you can do is you really can't have an anion interstitial, right? Because the anions are much larger than the cations. But you can have a cation interstitial. You can't have a cation vacancy and an anion vacancy. So in ceramics, you just can't say a vacancy is a point defect. What you need to be doing is identifying what that, whether it's an anion or a cation that's leading to that defect. So these defects, they're either point defects. We keep stoichiometry. Stoichiometry is basically where we keep that exact ratio of cations to anions. So when you talk about something that's stoichiometric, it has the same number of cations to anions as the chemical formula. You can deviate from that, and that's called non-stoichiometry. And some ceramic materials, especially those that have different valence states, and a great one is iron exists in multiple valence states. So we can have the structure change, we can have the equal number, and we really want to maintain electroneutrality. We can have these point defects with these defect structures, but there's two primary types of defects in ceramics we're going to really concentrate on here: a Frankel and a Schottky defect. In both cases, they maintain electroneutrality. So there's no charge, no change in charge, no charge added or taken away. So in the Frankel defect, what you have is a cation going into an interstitial. It's basically a Frankel defect. Will look like that cation interstitial. A Schottky defect is a vacancy pair. So we're maintaining charge neutrality, and Schottky defects are primarily found in these AX materials. What we tend to see is we take an anion and a cation vacancy. They're combined. So they need to maintain charge neutrality. In the Frankel defect, it's just that cation interstitial, or cation moves into one of these interstitial spaces. Charge neutrality is maintained in both cases, but what we have are these types of defects, and they can lead to some unique types of properties that we may run into. Once again, we can use that Arrhenius type relationship to tell us what the equilibrium number of defects would be as a function of temperature. Very similar to vacancies, very similar to diffusion. Still using this exponential to the negative activation energy over KT. The 2 is here because we have 2 defects, but what we tend to see is it's that same type of relationship that we have seen in the past. And for T is absolute temperature, remember to always keep T in units Kelvin. So we have these different types of defects that we can work with. And so that sort of gives us that background on the structure of ceramics.